Hello and welcome back to Miles Maths. This particular video is on transformations of graphs. It's the second video on this topic, and this is on stretches of graphs. So we're going to start off by looking at y equals x squared. So we have the graph on the screen here. It's courtesy of Desmos, which is a wonderful app. And let's have a look at what happens if we produce the graph of y equals 2x squared. Well, let's just consider a couple of points to begin with. If we have the point 1, 1, clearly that works. 1 squared is 1, so y is 1 when x is 1. We'd have a point here. If we take that point and we use y equals 2x squared, so we double it, we get 1 squared is 1, times by 2 is 2. And so you'd expect this point to end up here. Similarly, if I look at the point 2, 4, I'd say, well, if x is 2, 2 squared is 4, times the other 2 gives me 8. So this point here at 2, 4 should become 2, 8. And effectively what I'm doing is I'm looking at kind of taking this graph and stretching it in the y direction. So let's just see what that looks like completed as a graph. There it is. And we can see there's the point 1, 2. There's the point 2, 4. Of course, minus 1 squared is also 1, and it's doubled is 2, and so we see the same thing on this side. And so it's like somebody's taken this whole graph and they've stretched it upwards. Now, the interesting thing here is we have an invariant point, a point that doesn't move, which is the point 0, 0. And all of these graphs that you're going to see will have an invariant point. And because this graph is being stretched into the y direction, the invariant point will be on the x-axis. As we'll see, when we stretch in the x direction, the invariant point will be on the y-axis. So we're going to stretch this upwards, and it's a scale factor of 2. So anything that was at 1 is now at 2, anything that was at 4 is now at 8, anything that was at 1.5 is now at 3, and so on. So if we have a look then at what happens when we have y equals 2x all squared, well, you get a kind of a similar looking curve. If I put the two on together, you'll see that actually y equals 2x all squared, so we're multiplying by 2 before we're squaring, has actually been stretched, appears to have been stretched even further. In fact, however, this is not a stretch in the y direction at all. In fact, if we look at this point here, and we're looking for, bear in mind, for a scale factor of 2, you know, in the first case where we had 2x squared, we were doubling everything in the y direction. Here we can see that this point here is now actually here, and we've actually halved. So rather than it being at 1, 1, it's at a half 1. Okay, let that sink in for a second. So this point that was at x is 2, y is 4, 2, 4, is now at 1, 4. I've halved the x value to get the same y value. Okay, so this is effectively a stretch. However, the stretch is kind of inwards. Some people call it a compression, but we've effectively stretched it. We still call it a stretch in actual fact, by a scale factor of a half. So because it's a 2x squared, we say it's a scale factor of a half. I've got to pick the right Desmos here. I've got several of these open. There we go. So this is a scale factor of a half, 1 over 2, but the stretch is in the x direction. So what we can say from this is that if the 2, the multiplier, is outside of the function, in other words, we're not squaring the 2, we're only squaring the x squared in 2x squared, then it is in the y direction by a scale factor of 2. In other words, it does exactly what it says on the tin. This is exactly what the same way it is when we look at translations. In translations, when we're adding a number on, it's in the translation is in the y direction, and it's by the number that we're adding on. This is a multiplication, and it's in the direction, it's in the y direction. So outside the function, it's in the y direction, it does what it says on the tin. Inside the function, so we're squaring the 2 and the x squared, we see that it's the opposite of what we'd expect, and it's in the x direction. So rather than multiplying by 2, we divide by 2. It's a half. It's a scale factor of a half, and it's in the x direction. So once again, there's an invariant point, but we notice the invariant point is now, well, actually, it's on both axes because it's the origin. But let's have a look at some other curves and see what happens with these. So here is the curve y equals x squared minus 2x minus 1. So what would we expect to happen if we multiply the whole thing by 2? We've put the whole function in brackets and we're multiplying it by 2. Well, if we're multiplying it by 2, we would expect to see a stretch. The 2 is outside the function, so we'd expect it to be in the y direction, okay? And we'd expect everything to be multiplied by 2. So the question is, where's the invariant point? Is it on the x-axis or the y-axis? Well, the answer is it's on the x-axis. In other words, we're stretching from this line. So this point here at minus 1, 2, is now going to end up being stretched away by a scale factor of 2. So it's going to end up at minus 1, 4. So we're going to be expecting to see the new curve go through minus 1, 4. Similarly, though, the minimum point down here, which is at 1, minus 2, we're going to expect to see that stretched away in this direction. So it's like we've grabbed both ends of the curve, and the x-axis is not going to move. So when I put this on, as you'll see, there we go. We get 1 minus 2. We said we'd have minus 1, 4, and there it is right there, minus 1, 4. So the invariant points are the points at which it cuts the x-axis. Those are points which don't move. But all we've done is we've grabbed it and we've stretched it. So this distance was 1. It's now, this distance from the axis to the minimum point here was 2. It's now 4, and so on. If we look at the other version of this, we're going to say that the 2 is going to end up inside the function. Now that means instead of writing x here, I'm going to write 2x. I'm going to have 2x all squared, and there it is. And here, instead of x, I'm going to have 2x. So I'm going to have minus 2 times 2x, because I'm replacing x with 2x. So here's my new function. Okay, I haven't expanded any brackets. Of course, if you expand that, you get 4x squared minus 4x minus 1. And if I draw the graph of it, well, what would we be expecting? I should have asked you that first. We'd be expecting a scale factor of a half. We would be expecting an invariant point on the y-axis because this is in the x direction. So do you notice where it cuts the y-axis hasn't changed? If you think about this quite logically, they both have the same, they have minus 1 on the end, so the y-intercept is minus 1 on both graphs. But we've compressed every point, so if you look at this, this is around, what, about 2.2-ish, and it's now exactly half that, yes? Actually, it's not 2.2, is it? I'm talking rubbish. It's 2.4-ish, so this is about 1.2. So we've halved everything. We've halved, there's the original graph. We've halved it. Pick some points where it intersects the axis really nicely. So we've got minus 1, 2 there. On this graph, it's minus a half 2. So all the x coordinates have been halved to generate this graph. In other words, it's a stretch of scale factor a half in the x direction. So outside the function, y direction, does what it says on the tin, it doubles everything. Inside the function, x direction, halves everything. Okay, so if we go and look at y equals x squared and we put the 0.5 inside the function, what are we expecting to happen? We've got 0.5 x squared and it's inside the function. If it's inside the function, it does the opposite of what we're expecting. So 0.5, if we were halving x, it's actually going to stretch it by a scale factor of 2. So let's have a look at it. So we're expecting this to go by a scale factor of 2 in the x direction because it's inside the function. So here we go. I'm going to double everything. So here I've got the 0.24. It's now going to be the 0.44. So 2. It's now gone out to 4. We've doubled this distance. And that will work with every other point on the graph. If, however, I have 0.5 x squared, 0.5 just x squared, there's no brackets, the 0.5 is outside of the x squared function. I'm going in the y direction, but I'm going half. I'm halving everything. So where this point's at 2, 4, this point's going to end up at 2, 2. And you can see that really clearly. There it is. There's the point 2, 2. It's going to go through the point 2, 2. So it's going to push the function down. This works for, obviously, for everything. So if we have a look at, this is the original function, y equals x cubed minus 3x squared plus 2. Cubics are no different. We can either multiply this by 3 on the outside of the bracket, on the outside of the function. This will be in the y direction. So when I look at this, this point here that's at 0, 2 is going to end up at 0, 6, because I'm stretching it in the y direction. This point that's at 2 minus 2 is going to end up at 2 minus 6 because I'm stretching it away from the axis. And the 3 intercepts on the x-axis here, the 3 roots of this polynomial, are going to be invariant points because we're stretching away from this axis. So let's see what it looks like. Here we have the 3 invariant points. Here we see it's at 2, 6. Here it's at 2 minus 6. Okay. So last one. Here we have the 3 put inside the function. So we're looking at this function here, and I'm replacing x by 3x. So instead of x cubed, I've got 3x cubed. Instead of minus 3x squared, I've got minus 3, there it is, 3x squared, because I'm putting the 3 inside the function. So what should happen? Well, I should be looking at a stretch by a scale factor of 1/3 in the x directions inside the function. So it's in the x direction. It does the opposite to what I think it should do. So it should go in the x direction, and the invariant points will be on the y-axis. In other words, the only invariant point will be here at 0, 2. This will go through 0, 2. So I'm now going to, I can pick something reasonably nice here, I hope. Can I? Possibly not. Okay, let's just show this and see where we are. Okay, so here I was at this minimum point at 2 minus 2. As this is 2, if you divide that by 3, we get 2/3. So this should be at 2/3. Well, it's just over 0.5. It's about 0.66. You can see that's correct. We can see that 0, 2 is the invariant point. So we can see this as if you like, a compression. It's actually a stretch. We describe it as a stretch by scale factor 1/3 because the 3 is inside the function.
Okay, let's have a quick look at some examples of how we do typical stretching graph type problems. Here is a graph of f of x equals x squared. Sketch the graph of f of x equals 3x squared. Well, the 3 is outside the function, so we should know that this is in the y direction. And all we need to do is take some points that we can see. We know this is stretching away from the x-axis, and that therefore this is an invariant point. However, we can look at the point 1, 1, and we know we're stretching away. So we're stretching away by a scale factor of 3. So we'll be going through the point 1, 3. Similarly, minus 1, 1 will become minus 1, 3. We know this is invariant, and therefore we can just sketch on our new graph. It's only a sketch, so it doesn't need to be too exact. Now, I've done this in pen. You would do this on a GCSE exam. You would do this obviously in pencil. I'll just colour code that as being purple. Sketch the graph of f of x equals a half x squared, and the half is inside the brackets, inside the squared function. So we know that this now is a scale factor of 2. Because this is in the x direction, it's inside the function. It's going to be inside the function, it's the x direction, and it's the opposite of what we would think. So rather than it being a half, it's actually a scale factor of 2. So again, I can take some points on my original graph, and I can say, well, this point's invariant, so it stays where it is. I'm, however, going this way. It's invariant, by the way, this time, because it's on the y-axis, and we're stretching away from the y-axis in both directions. So scale factor of 2, the point 1, 1 becomes the point 2, 1. We're going to go through that point there. And the point minus 1, 1 becomes minus 2, 1, and we're going to go through there. None of the other points are actually going to fit on the curve. This point actually goes through 1.4, so that will actually go through 2.8. Will I be able to get that on? Yes, I will. It's there. So we'll just try and go as accurately as we can now. It's coming down something like that through the origin and kind of back out the other side. And that's my second graph. Second example. F of x is root x shown. Sketch f of x equals 2 root x. Okay, so the 2 is outside the function. That means it's a stretch in the y direction. So I should be able to just look at this and say, well, if I'm going through 1, 1, I must be going at the stretched version of this would be a stretch in the y direction. So I must be going through 1, 2. Here I've got the point 4, 2. So this again will be stretched by a scale factor of 2. So I must be going through the point 4, 4. I'm stretching away from the x-axis. So any point that's on the x-axis here is invariant. So it doesn't move. And I can just sketch that in kind of like that. And there's a sketch of, you could put it on there actually, y equals, or f of x equals 2 root x. You could label this if you wanted to. The next one is f of x equals root of 5x. The 5 is inside the function. If it's inside the function, it's the opposite of what we think it is. So it's not 5, it's 1/5. It's also in the x direction. So this is a stretch, scale factor 1/5 in the x direction. So if I take a point that I know the location of, like the point 1, 1 here, well, 1/5 of 1 would be 0.2. So this point is actually going to end up here. This point at 4, 2. Well, 1/5 of 4 is 0.8. So that's going to end up there. And I'm actually not going to be able to do any more. There's no other points I can really locate easily. I know, obviously, I'm stretching this time. We are stretching in the x direction. So anything on the y-axis, this point here is on the y-axis, is invariant again. So I can just sketch this something like that. And this will be the line y equals root 5x, where we're all inside the function. So there's a couple of quick examples. Let's take a couple more so you get a real sort of flavour for what GCSE problems or these sorts of questions at a GCSE level look like. The graph of f of x equals x squared minus 4x is shown. Sketch the graph of 2f of x. There's an extraneous bracket got in there somehow. So 2f of x, well, the 2 is outside the function. Therefore, this is in the y direction. I know that any points on the x-axis, therefore, will be invariant. So this point here and this point here will be invariant. I know that this point here is at the point 2 minus 4. So this will be stretched, and it will be 2, and minus 4 doubled is minus 8. So 5, 6, 7, 8. So we're going to be going through that point there. I'm then going to be going and taking this point here is at minus 1, 5. That will be stretched by a scale factor of 2. to minus 110. This point here is at 5, 5. This will be stretched away to 5, 10. So I've now got to just draw a parabola that goes through all of these points. And this is quite tricky. But remember, they're asking you, and it says sketch. Doesn't say plot the points, it says sketch. So we haven't drawn a table of values, and our sketch is going to be a little bit rough through there. But that's satisfactory. That the intent is there, that they can see that you know this has been stretched, that it's stretching, it's inside the curve here, it's off the bottom of the original curve there. That's going to be absolutely fine. Let's have a look at the second part then. And again, you might want to label that as 2f of x. This is f of 2x it now wants us to sketch. Good. Well, the 2 is inside the function, so the scale factor is a half, and this time we know the stretch is in the x direction. So I can start to pick out a few points like I did before to give me an idea of what this looks like. And I remember I'm going to do this according to the x axis. So this point here is at 4, 0. It's therefore, when I take a scale factor of 2, going to end up being at 2, 0. I'm going to end up being there. This point is on the y-axis, so it's invariant. So I am going to still continue to go through that point. The minimum point on the curve down here is at 2 minus 4. It's 2, so I'm going to halve that distance. I've got a scale factor of a half, because remember, the 2 is inside the function, so it's a scale factor of a half. So I'm starting to see a quite narrow curve here. I can now start to maybe work on a few more points. This point right up here, look, is at minus 2, minus 212 by the looks of it. So that will be at minus 112. And this point here, it seems to be at 612. And so that would be at 3. Half of 6 is 3. And there, once again, I have enough points to kind of begin to develop a sketch of this this particular function. Really not easy doing this on camera like this. And this blue function is y equals f of 2x. The sketches aren't beautiful. They'd only ask you usually to do 1 on a diagram at GCSE, not 2. This is just for demonstration purposes, really. And obviously, you would use a pencil. And finally, our fourth example here. The function f of x is shown by the solid line on the diagram. Oh, that's interesting. Good. And it's transformed to make a second function shown by the dotted line. It doesn't scan very well. Circle the function which represents the dotted line. Okay, so I've got this line here, and clearly I've got a transformation where this line's been transformed into the dotted line. All I have to do is work out which one of these it's going to be. So the question is this in the x or y direction to begin with? Well, let's have a look. Let's consider the minimum point. And we'll actually consider the points where it crosses the axes as well. Have the points where it crosses the x-axis changed? No. So these 2 points are invariant points. If they're invariant points on the x-axis, this must be a stretch in the y direction. I can check that by checking the intercepts on the y-axis. Are they different? Yes, they are. Therefore, we know this isn't a stretch in the x direction. The invariant points are on the x-axis. It's a stretch in the y direction. Good. I can now have a look at this minimum point. At the original, on the original graph, this would be at. And I can write all over this. I mean, you write all over stuff. It's kind of a good plan. So this point here is, it would seem at 4, minus 9. I've got a minus on there. 4 negative 9 if you want to be more precise. So I can just have a look at where this is. Well, this seems to be at 4 minus 4.5. So what's happened? Well, it's half. 4.5 is half of 9, or minus 4.5 is half of minus 9, I should say. So I'm expecting a number that's outside the function. It can't be b and it can't be d. This would be doubling. This is halving. Must be c. And that's just some typical examples that you might find on a GCSE paper.